In this video, we'll discuss the significance of a great equation of mathematical physics called Laplace's equation. First of all, let's look at some of the equations that we already know from before. For example, Gauss's E law in terms of a vector potential phi can be written as the equation known as Poisson's equation, which is the Laplacian of phi equals 4 pi rho, where rho is a charge density in space. Then you have the wave equation, which is the Laplacian of phi equals 1 over v squared times the double derivative of phi with respect to time. So here phi is a function of x, y, and z. Here phi is a function of x, y, z, and t. And here the heat diffusion equation tells us how heat travels through something like a bar, or molecules diffuse through a volume of solution. So that tells us the Laplacian of phi is 1 over alpha squared, known as the diffusion constant, times the first derivative. So the big difference between the wave equation and a diffusion equation is the order of the time derivatives. Here things do decay. Here, so heat does become eventually cold, whereas the wave equation, the wave somehow renews itself over time. So these are the various equations. Now, what they all have in common is that if you don't have any sources and you have what's called steady state, then they all boil down to the following equation: del squared phi equal to 0 under some boundary conditions. This equation is of paramount importance in mathematical physics, and it's called Laplace's equation. And that's what our video is about. Actually, a lot of mathematicians who work in harmonic analysis deal with Laplace's equation, and that's the only equation they look at their entire lives. So you can see the tremendous importance of this equation is such that an entire mathematical branch is developed. Normally these workers live in n dimensions, but we'll confine our attention to three-dimensional space in this video. So suppose you have a neighborhood of some point x naught in three-dimensional space. So x naught, for example, would be x naught 1, x naught 2, and x naught 3, or x, y, z. Okay. Now what we're going to do is, this U stands for a neighborhood. So we'll look at a little neighborhood of this point ux naught, which means that if you have the x naught point, we're looking at all the points within a certain distance from the x naught point. So you have some point x there. What can you say about that point? Well, for one thing, you can Taylor expand this function phi that satisfies Laplace's equation as follows. Phi of x would be some phi of x naught plus I get x minus x naught dotted with a gradient of phi evaluated at x naught. And then, now this is going to look weird, but I'm going to get x minus x naught transpose with a two-dimensional matrix del 2 phi over del x I del xj evaluated at x naught dotted with x minus x naught without the transpose plus higher order terms. Now that's the state of affairs. This matrix, this by the way is Laplacian. If you can diagonalize this matrix, you get a Laplacian operator. This is called the Hessian matrix. So if we go to coordinates known as the normal coordinates, then we can diagonalize this Hessian matrix. Right now it has all kinds of components. For example, you can have del x1, del x2, So if I write out the Hessian matrix, it could look like this. And I'll use subscripts to denote the partial derivatives. So I could have phi 1, 1, I could have phi 1, 2, which is the same as phi 2, 1 by Clairaut's theorem, and then phi 1, 3, which is the same as phi 3, 1 by Clairaut's theorem, phi 2, 2, and phi 2, 3, phi 3, 2, and phi 3, 3. So this could be the general state of affairs when you have a full-scale Hessian matrix. But what we're going to do is we're going to go to what coordinate system known as normal coordinates, and I won't prove it to you, but normal coordinates can always be found. And in the normal coordinate system, all these terms, we're going to diagonalize the matrix so that you only get phi 1, 1, and because it's a new coordinate system, I'll probably call it tildes, 0, 0, 0, phi 2, 2, tilde, 0, 0, 0, phi tilde 3, 3. And now it's the legitimate Laplacian in those coordinates. So assuming we have found those coordinates, those tilde coordinates, what I'm going to get is I'm going to get the average value of this function, which I'll call phi tilde bar, is going to be phi tilde at the origin plus some constant c, which comes as a result of the normalizations, and the Laplacian of this phi tilde at the point 0, and the higher order terms can be neglected. So this tells us something very important about the Laplacian. The Laplacian under those normal coordinates is proportional to the difference of the function minus its average. I'll omit the tildes, assuming we are in normal coordinates. So the Laplacian of a function is the difference between the average value in a neighborhood minus the value at a certain point. So let's think about some consequences. Suppose the function satisfies Laplace's equation. Suppose del squared phi is 0. Then it tells us that the value of the function at any point is equal to the value that's average. So that's an amazing property of the Laplacian. If your function satisfies the Laplace's equation and you want to find the value of the function at any point inside a neighborhood, you don't have to. You can just set it equal to the average value and you will not be wrong. So it's a pretty amazing result that in itself. It means that if you have a black hole here and you want to find the value at the black hole, you don't have to. You can just find all the surrounding areas, take the average value and set it equal to that. That's one of the beautiful results of harmonic analysis. The other result is this. If you have a function that satisfies Laplace's equation, you cannot have any peaks and valleys. It cannot have any maxima or minima, only saddle points. So the reason for that is if you have a maximum at a certain point, that maximum point will be higher than all the other points around it. So you cannot have a maximum, because I've already shown you that the value at any point is equal to the average value. So if you have a maximum, the value of the maximum point is going to be bigger than all the other surrounding values. So this cannot possibly be true. Similarly, if you have a minimum, that will be less than all the surrounding values. So that also cannot be true. So the only kinds of behavior you can have are saddle points, which means that the Hessian matrix must have both positive and negative eigenvalues. So if you actually find the eigenvalues of this Hessian matrix, you'll find that it's in 3 dimension. It's got either 2 positive eigenvalues and 1 negative eigenvalue, or 1 positive eigenvalues and 2 negative eigenvalues. It cannot be all positive or all negative, because all positive will correspond to a maximum and all negative will correspond to a minimum. Well, those are some of the properties of the Laplace's equation. Now, I won't bother talking about other properties. There are many, many more properties, but just keep in mind that Laplace's equation is very important, and if you solve Laplace's equation, the solution to these other things with time is not that difficult. Solving the Laplace's equation is far more difficult than solving these associated equations. So when we investigate the heat equation in detail, we'll find that there's a different equation that comes associated with it called the Helmholtz equation. So that will be the eigenvalue problem associated to this particular equation. So you can always have an eigenvalue problem that comes from just the consideration of Laplace's equation.